Hey everyone, so I wanted to make a quick video because there's no Calc Center today, and even though the worksheets got postponed, if you got time, you can knock it out today. So, do a quick worksheet topic recap. I will talk about MATLAB code. I'll try and mark the timestamp in the YouTube video, so if you want to just skip that, that's fine. But okay, real quick on linearization. So, we have that x prime and y prime are equal to, and then we have, we'll call this function f of xy and this function g of xy. Okay, so I'm just gonna say this is equal to f and g, right? And realize what I have not written in both cases is that this is a function of x and y, and this is a function of x and y, and so on, right? But implicitly, we sort of know that in the back of our minds. Okay, if you want, anytime a math thing talks about linearization, they always mean the same thing. They mean that where you are, if you move a little bit, is approximately where you used to be. So I'll write this as f and g, and now I'll emphasize this is evaluated at some spot xy, but this is evaluated at the spot you used to be. Okay, so we're trying to approximate this value using this value. So where you used to be, I'm going to call AB plus, and then you do whatever the first derivative is times the change. And when I say whatever the first derivative is, in Calc 1, it's just the derivative. In Calc 3, it's the gradient. And what we're going to use as the gradient is just that we need a matrix because we have more than one function. So the first row of our matrix is going to be grad f, and the second row is going to be grad g. In other words, the first row is the partial of f with respect to x, then the partial of f with respect to y, and if we had another variable, we could just keep on going forever and ever and ever, okay? We only have the two variables, so let's take the partial of f with respect to x, and I'm going to rearrange it a bit, so I'm going to write it as ry minus 1 minus 2x. And then I'm supposed to do the partial of f with respect to y, and I get rx. Okay, and so this row here is the gradient of f. So now let's go down to the next row. We're going to do the gradient of g, and there's no x's appearing in g, so the partial with respect to x is 0. Then the partial with respect to y is 1 minus 2y. Okay, and this matrix right here is the Jacobian. And notice it is a function of x and y. Okay, and just like with our start vector, how you plug in the point you know about, we're also going to plug that in here. So ultimately, I'm going to want to evaluate this at the spot AB. Okay, but for now, it's just, I'm going to leave it in terms of x and y. And then, so this is a matrix, so I multiply it by my change vector. So this is a, oops, other way, gosh darn it. Other way. There we go. Change in x, change in y. So this is going to be x minus the a value, y minus the b value. Okay. So let's use this. One of the equilibrium points for this system is the point 0, 1. You can check if you plug in x equals 0 and y equals 1, that you'll get dx dt is 0 and dy dt is 0. It's pretty easy to see because plugging in x equals 0 kills everything up there, and then plugging in y equals 1 will kill this thing. Okay, so this is going to play the role of AB, the point that we know stuff about. And so if I were to plug that in, then, let me also say, I write f and g because it's what we're used to. But I actually don't need to write this at all. And instead, I can say the derivative you care about at a new point is approximately the derivative at an old point, x prime, y prime, at this point, plus, and then this change. Okay, now we're going to use AB equals 0, 1. So let's plug in 0, 1. Okay, and the whole reason we do that, if I plug in 0, 1 into my equations for x prime and y prime, hey, here they are, I'm going to get 0 and 0. So what this becomes is 0, 0 plus, And we need to plug it into the Jacobian. So this is going to be a 0, 1. All right, plug in 0 for x and 1 for y. We have r minus 1, 0, 0, minus 1. And plug in 0 for a and 1 for b. We have x and y minus 1. Okay. So the derivative, the velocity vector, is approximately, and you know what, this 0 vector here, we don't need to write it. It's like writing 2 plus 0. Why would you write plus 0? So we can actually clean this up even more. And we can say, okay, so x prime y prime is approximately, and then we have this. Okay. And that looks just suspiciously similar to velocity vector is matrix times position vector, which is what we did last week, right? Or it's what was due last week. So the claim is that you can understand the behavior of this equilibrium point by analyzing this matrix, which is the Jacobian, and I plug in the equilibrium point. Okay, so let's analyze it a bit. So if we use r equals 1.2, then all that really matters is that this value is something positive, and this value is something negative. And so in other words, right here is the equilibrium spot that we care about. It's 0, 1. Okay. And in the x direction, we would flow away from the equilibrium because this value is positive. And in the y direction, we would flow towards the equilibrium because that value is negative, or the eigenvalue is negative, which means our net flow is going to look something like this. Okay. And most importantly, all of what I just said is only true near the equilibrium point. Okay. Near the this is intentionally vague. This is when we get to use this approximation. And so we should imagine that if we plot something, we have to zoom in a bunch and then we'll see this behavior. Okay. So now I'm going to hop to the MATLAB portion and we'll see this in action. All right. So stop share. And now we'll share the desktop. Go. Great. Sweet. So if we were to plot our vector field, then here's the code provided by Young Cheng. And well, okay, I tweaked it a little bit. So all right, what's going on? The code provided is for a linear system. So it would be this matrix here, which he then references to build the dxdt and dydt. Now, he didn't call them dxdt because MATLAB wouldn't like that, so we called them u and v. But that's what's going on here. So with u, I just input what our dxdt equation is. So it's rxy minus x squared. And similarly with v, I just put in what our dydt equation is. And if I did nothing else except change that, then let's go ahead and run it and see what we get. Boom. Okay, so this does not demonstrate, like, from looking at this, if I go to 0, 1, so approximately right here, I can't tell what's going on. Now maybe MATLAB's nice enough where if I zoom in, yeah, I'm not even going to try. Let's just make it work. So roughly speaking, I would say go to a scale of 1/10 anytime you need to be near something for linear approximation. That's just because the problems we give you tend to be kind of nice. And if you're at that scale, it tends to work out kind of nice. There's nothing deep and mathematical that I'm saying there. I'm just noticing patterns about, choosing nice stuff. So let's go ahead and get rid of when we plotted -5 to 5 on this square. And instead, we want to be near 0, 1. So my x is going from -1/10 to +1/10. And my y is going from 1 - 1/10, so 0.9, up to 1 + 1/10. Okay. And if I only change the mesh grid, and I don't mess with these x limit, y limit, you'll instantly know that something else is wrong. There we go. Because what you're going to get is a little box that's plotted inside of a big block of just blankness, right? There it is. So this is essentially the area we're trying to zoom in on. Okay, so let's tell MATLAB, you know what, I had the wrong x limit and y limit. Let's get a nice plot going here. And while it loads, I'll just say, remember, we're going towards it in y and away from it in x. And that's exactly what we see. Down and to the right, down and to the left, up and to the left, up and to the right. And so here's our equilibrium spot 0, 1. And, you know, this matrix is describing how points are going to move around. And if I go back to sharing my screen on the equation, we have the Jacobian, which was this r minus 1, 0, 0, minus 1, times the change vector, which was x, and then y minus 1. But, you know, don't let that confuse you. Really, it's just if I have a spot like over here, and hopefully my cursor shows up, then there the y value is 1.04. And the way this point moves is just determined by the 0.04 part. So essentially what's happening is the dynamics are kind of like shifting your equilibrium point to be at 0, 0. And so now when you measure where you are, you're just measuring it from, in this case, it's from 0, 1. And then if I go up here, I just have the little change in x and change in y rather than the full position. But, you know, even if that doesn't quite make sense, don't worry about it. The point is we can zoom in on the equilibrium point and we get the dynamics that we were hoping to get. Okay, so hopefully you can do the other problems. Now, if we hop over to Euler's method, let's look at what's going on here. So, all right, very similarly, not have to think about what A, B, C, and D are doing. Don't worry about it too much. The only point that I want to make is, look, this F and this G, they're going to play the role of dx dt and dy dt. Okay. So knowing that, if we just kind of hop down for a bit and we look at what's going on in this for loop, okay, he's saying your new x position is your old x position. In fact, let's write this. X new is equal to x old. That should be commented out, sorry. Commented out. Plus dx dt times dt. Like essentially this is what's happening. It's where you start plus your velocity times a little bit of change in time. And so my f function, that is my dx dt, right? So you just have to use the proper f function, and then this should discretely jump around to model the x behavior, and you do it similarly for y, and then it'll plot the curve for you. So I'm not going to run that one. You should be able to play around a bit now that you saw the other video. If there are issues, then hopefully we just sort it out tomorrow in Calc Center. All right, so let's turn this off, and I'll see you next time.